All right, p-values, and what do they mean in terms of a hypothesis test or a significance test? Here's the idea. Every single hypothesis test will always start with a null hypothesis in which we say we believe, or someone is claiming, that the true parameter, the true p or the true mu for something is equal to something. Mu equals 10. P equals 0.75. There will always be a null hypothesis in terms of mu or p that says, you know what, this is the value that we're starting at. This is the claim. Then there will be an alternate hypothesis about that same parameter, about p or about mu, that says, but we're suspicious it might be lower than that, or we're suspicious it might be higher than that, or we're suspicious it's something different than that. One way or the other, it's going to be one of these three for the alternate hypothesis. In both, no matter what though, in both cases, we're always talking about a p or a mu, a true parameter from the population. And so those will be the things that we'll talk about in sections 9.2 and 9.3. 9.2 will be about proportions, and 9.3 will be about means, but they both follow this same logic. Both of them are about parameters. Here's what we know about parameters. We can find the sampling distribution of all the p's or the mu's, all the possible p hats or x bars that could come from a population, because of what we learned in chapter 7. Now, this picture, you have no idea how long it took me to try to draw this, but that's another story. This picture is really made up of an almost infinite number of dots. Every dot represents a different p hat or x bar that could have come from a population that has this mu or this p, right? So we end up with an almost infinite number. We have a cajillion dots here, a cajillion data points. This is every possible p hat that could happen if the true parameter, the true mu or the true p, really is what's stated here. We know that all the p hats and the x bars are going to come around there somewhere. And so to test our hypothesis, what we do is we go out and we take one sample. We find one p hat or one x bar. And then we say, where does it fit into this world that I expected? Where do I think that one fits? Where does that one fit in with all these others that I think these are all theoretical? But then I come along and I say, I took this one sample right here and I got this, that blue dot. Hopefully that shows up as a blue dot right there. We say, oh, this blue dot kind of fits in with the context of the other red ones. And I go, you know what? That's not super surprising if I get that right here. If my p hat had turned out to be way down here, I hope that yellow dot shows up, you say, wow, that's really surprising. If this is what I expected to happen, and this is what really happened, that's surprising to me. And I go, that makes me suspicious. The way that we measure how likely or unlikely was that one sample that we took is this thing called a p-value. I'm going to try to draw a blue line through that blue dot. Oh, good. Perfectly straight line, Rex. Good job. If this is really normal, what we can do then is we can use our norm CDF and say, hey, what's the chance if this is the world that we believe from the null hypothesis, what's the chance that I would pull one sample and I would be there or lower? This probability is called the p-value. The probability that I pulled one single sample that's that extreme out of this world, that's the p-value. For the blue one, there's quite a bit of area in that blue part. For the yellow one, if you can remember, if you can see it, my yellow dot was down here. This area down here is really small. The yellow area has a really small p-value, a really small probability of happening. The blue one has a higher probability of happening. This part of the lesson is about how do we quantify that. We're going to calculate them in sections 9.2 and 9.3. This part of section 9.1 is about how do we read those and what does that mean. So here we go. Interpreting p-values. Now we'll see how this works. When we assume that the null hypothesis is true, the statistic that would take a value as extreme or more extreme than the one actually observed is called the p-value. In other words, what's the chance that I would pull a p-hat or an x-bar that far out in the tail if the null hypothesis was really true? A small p-value, which means I was way out in that tail, says, makes me think maybe that null hypothesis wasn't true. A large p-value, which means I was back in the body of that normal curve, I wasn't out there in the tail so far, so the p-value is higher, it says, maybe that gives me evidence that the null hypothesis really is true. Stick with me on this. This will work, right? It's weird at first, but it totally makes sense. The two things that we will do is we will either reject or fail to reject the null hypothesis. If we have a really, really small p-value, we're way out there in the tail, we go, dang, that's weird. I guess that null hypothesis must have been something suspicious, so we would reject it. Or if we're in the body of that normal curve where it says, you know what, yeah, this falls within what I think might have happened. If the null hypothesis is true, we don't accept it. It doesn't prove the null hypothesis. It's simply not enough evidence to reject it, so we fail to reject. You're either going to reject the null hypothesis or you're going to fail to reject it. Just like if you go on trial, you're either going to be found guilty or not guilty. You won't be found innocent. Being found innocent would be like accepting the null hypothesis, and we don't. So, down here on the bottom, and that I can't get that thing to go away, but if I just wait a second. In a nutshell, our conclusion will always come down to this. If the p-value is small, we reject the null hypothesis and we say, hey, I must have evidence of that alternate hypothesis. I guess it was really lower than that, or I guess it was really higher than that, whatever the alternative says. If the p-value is large, then we would fail to reject the null hypothesis and we say, you know what, I don't have enough evidence to prove that it's less than or greater than what we thought. So I guess we still have to go with that null hypothesis. Now, if you're sitting there going, wait a second, who decides what's small or large? That will be coming later. Because a small number, what's a small number? It depends on your context, right? So we'll talk later about who decides what's a small p-value or what's a large p-value. But for our purposes right now, here's almost the same picture again, with one more thing. It says this, there is no rule, and again you can read, there's no rule that says what a small p-value is, but what we do is, before we start the problem, before we even start, somebody, whether it's you as the researcher or your boss, is going to say, hey, we're going to do this at this significance level. And what that is, this is the Greek letter alpha. The Greek letter alpha says, you know what? If you get a p-value below this number, we're going to call that low. We have to set our line before we start the problem, because otherwise we go, I don't know, does that seem small to you? It's kind of small. It's not that small. What do you think? And you're asking all your friends. So this is before we even start. We say, you know what? We're drawing our line. And the most common line is at 5%. A p-value below 5%. So, and we'll talk more about this as we get into 9.2 and 9.3, but if the alpha level isn't told to you, then you say, oh, I guess I'm going to use 5. If the p-value is smaller than alpha, if it's low as compared to alpha, then we say we're going to reject the null hypothesis. If it's not low, we fail to reject. So that brings us down here. Before we start the problem, we say what alpha is. If the p-value is less than alpha, we reject the null hypothesis. And we say, yep, I have evidence of the alternate. If the p-value is greater than or equal to alpha, we fail to reject. And we say, I can't conclude that in context. Okay? Here's the inappropriate but maybe helpful little rhyme. If the p is low, reject the null hypothesis. If the p is low, reject the null hypothesis. that will help you, maybe that will help you remember it. So here's an example, right? Company has developed these new AAA batteries. They're supposed to be longer, but we don't know. However, these new batteries are more expensive. So it's like we can't just go ahead and start making them because they cost us more to make them. So we want to be sure. Based on experience, they know that their regular AAA batteries before were 30 hours of continuous use. Company takes an SRS of 15 new batteries and uses them continuously until they're drained. So they're going to do a significance test. They say the null hypothesis is that the new mean is really 30 hours. You know what? First battery, second battery, third battery, we see how long they lasted. Add those up, divide by 15. We think, the mean is still really 30. What we're secretly hopeful of is that the alternate hypothesis, maybe the new mean is bigger than 30. That's what we're hoping for. Mu is the true mean lifetime of the new batteries. The resulting p-value is 0.0276, right? Which means somebody did this. And they said, you know what? Our new batteries, our tail, we were out, let's see, we got something here bigger than 30. We were out here where this probability, the probability of being in that tail is 2.76%. I would have expected 30, but I got something out here. We don't know anything about these calculations yet. That's coming in chapters or sections 2 and 3. But what it's saying is we were out here in this part of the tail. If before we started our test, somebody had said, you know what, your line for a low p-value is 0.05. You say, hey, is 0.0276 a low number? Well, compared to 0.05, it sure is. Since the p-value is less than 0.5, if we had said that, if somebody before this test had started had said the alpha level that we're using is 5%, this p is low. We would say, I would reject the null hypothesis, and I have evidence that my new batteries are better than 30-hour batteries, right? If the significance level that we picked is 5%, we win. Our new batteries are better. But if somebody had said, you know what, we have to be so sure about this. We've got to be so far out there in that tail that there is no other solution that's possible. We're going to use alpha equals 1%. Now we say, hey, is that p-value, is 0.0276 a low number? You go, well, it's kind of low, but it's not low compared to 0.01. It is not enough to reject the null hypothesis. And so we go, this doesn't give us strong statistical evidence that our new batteries are better than 30 hours. We would fail to reject the null hypothesis, which would say, you know what, we don't have proof yet. The lower the alpha level, the harder it is to prove something, the harder it is to reject the null hypothesis. You've got to be further out in that tail for it to make sense. As we go through these, and as we get into 9.2 and 9.3, this will continue to make more sense. But bottom line, darn it, my picture went away. Bottom line is we build a world based on this assumption. We build a world based on that and say, this is what we expect to happen. Then we take one sample and see where it fits in this world. If it fits in here somewhere, we go, okay, we failed to reject this, and we go, all right, that parameter is probably legit. However, if we build this world based on this assumption and expect to be in here, but get a sample that's so far out here that you go, no way, that couldn't happen, we would reject the null hypothesis, and that would give us evidence that the true parameter is whatever the alternate says, right? The p-value is what determines that. If the p is low, reject the null hypothesis. If the p is not low, we would fail to reject the null hypothesis, and we would not have the evidence to support this. Stick with me on this logic. It does make sense, but it's goofy, but once it clicks, you go, oh, of course that makes sense. So stick with me. I promise this will work. That's it for p-value. We'll talk more later.